So first of all, I'd like to thank Hugh and Matt for inviting me to speak here today. This talk is really a response to some of the work of Hugh and his collaborators, some of which we heard about on the first day. Similarly, the next talk is also going to be a sort of continuation of that. What I want to do is present a framework, or perhaps the framework, if I'm being more bold, for discussing the relationship between concepts like locality and retrocausality. It's also a framework in which one can consider building toy models which might reproduce quantum theory, although I'm not going to actually do much of that in this talk. So what I really want to pin down is what are the relationships between these concepts. Okay, so first of all I'm going to start with some motivation. So my starting point for getting into this whole idea of retrocausality is the various no-go theorems that we have about quantum theory. The most well-known one, and the one we've already heard a lot about, is of course Bell's theorem. But I wanted to point out, although I'm not really going to have time to talk about them, that there's at least half a dozen other results which show that quantum theory has strange properties. So my way of understanding what these no-go theorems means is, well, it's similar to what Rob Speckens says about it. And I sort of alluded to it in my comment on Hugh's talk a couple of days ago. So the idea is that these no-go theorems, they expose explanatory gaps in our existing realist understanding of quantum theory. And those explanatory gaps take the form of the fact that we need fine-tunings to account for the observed quantum statistics. So in the case of Bell's theorem, in the conventional sort of realist understanding of that theorem, it says that there are non-local influences, but we also know that those non-local influences can't be used to send superluminal signals. And that's sort of, all things being equal, it looks quite puzzling, because if there really are things that go faster than the speed of light, then why can't I encode a signal on them? And of course, we have an explanation for that, which is that in any sort of underlying hidden variable theory, we would have to have uncertainty about the true ontological state of reality. So we'd have some probability distribution over that. And it just so happens that upon averaging over those probabilities, the ability to signal gets washed out, although the sort of influence of these non-local influences still appears in the form of Bell inequality violations. But the point is that if you take those probabilities and if you modified them just a tiny bit, then suddenly you'd find that the theory tells you can now signal, right? So those probabilities need to be precisely set, precisely fine-tuned in order to rule out the possibility of signaling. So similarly, I think all of the other no-go theorems can be cashed out in a similar kind of way. They're all about the fact that we end up saying that certain things must exist out there in reality, but their influence on the operational statistics gets washed out by averaging somehow, and you need a precise fine-tuning to do that. I should just point out that it's not really a new no-go theorem, but a sort of variant of an existing no-go theorem is going to be presented in the next talk. So how should we respond to the existence of these explanatory gaps? And I think there are basically three possible responses. The first one you can do is to just reject realism. That means adopting one of these sort of neo-Copenhagen type approaches, such as quantum Bayesianism, for example. Now, I would like to actually explain these explanatory gaps. I would like to close these explanatory gaps. And from my point of view, these approaches all, in some sense, give up on the notion of needing an explanation for things. They just sort of accept that that's the way things are. So I'm not particularly inclined to this particular point of view. The other thing you can do if you want to maintain realism is you can just bite the bullet in some way, and there are two sort of arms to that. One is to just say, yes, there are these fine-tunings in nature, that's just the way things are. It's similar to the sort of Copenhagen response, right? The other thing you can do is to say, and this is a much bolder thing to do, is to say, actually these fine-tunings don't really exist. We haven't seen any systems which violate them yet, but somewhere out there in the universe there's going to be systems which allow us to superluminal signal. And the idea is that there's some process, something like equilibration, like thermal equilibration, which is responsible for the fact that we don't see that in ordinary physical systems. So Anthony Valentini's approach to Bohmian mechanics, that's what this kind of thing says this kind of thing. Now this is I think this is a consistent position to take, but I think it's an extremely bold position to take, because of course we have no evidence whatsoever for violation of Lorentz invariance or the existence of preferred frames or anything like that right now. So although it's a consistent position, I think you have to be pretty bold to believe that. The other thing you can do is you can reject one or more of the assumptions that go into proving these theorems. So as John Bell said, the only thing that's proved by a no-go theorem is lack of imagination. So it means that perhaps there are assumptions in here, and some of them might be implicit, that when you get rid of them, you suddenly find, there's a consistent and coherent explanation. So for me, the reason why I'm interested in retrocausality is the sort of implicit assumption that there's no retrocausality is an obvious starting point here. Just because it's fairly easy to see how to formulate mathematically what it would mean for there to be a theory with retrocausality, and that's mostly what I'm going to do today. Whereas some of the other suggestions people have made don't make quite as much sense to me. So this is just one thing that we can do fairly straightforwardly. Now, since I formulated the no-go theorems in terms of explanatory gaps, in terms of these fine-tunings, for me, if not for Hugh, the explanatory gap that comes with retrocausality is important to address. So basically, why can't I signal into the past? Why can't I tell myself yesterday what the lottery numbers are today? So again, there's sort of two possible responses to this. People laugh when I say this one, but I'm actually serious. Basically, what we can hope is to put all of the other explanatory gaps now into one box, right? We'll only have to explain this explanatory gap, because when we go back to all of these features, what you can do is come up with generalized notions of what it means to be local, what it means to be non-contextual, etc., in a theory which potentially has retrocausality, and then you'll find that actually there can be theories which satisfy those assumptions. Okay, so you immediately get rid of all of these, and all of the problems are put into just this particular gap. But then that sort of seems to need an explanation in itself, and this is kind of speculative. So really, I'm talking about the notion of retrocausality, but I don't think that the notion of either causality or retrocausality is a fundamental physics notion. So what we're really talking about here is that we have some kind of theory formulated in the block universe in four-dimensional space-time. It has no a priori notion of causality or retrocausality in it. And that's a notion that's somehow emergent. So basically, what I'm going to imagine, or what I'm going to say, is that we should put all of these problems into thermodynamics. The fact that there's an asymmetry between whether we can signal into the future or signal into the past should somehow be explained in the same way as the thermodynamic arrow of time will put it into the asymmetry of initial and final conditions. So it's perhaps a bit of a cop-out, but we already have an asymmetry to explain, a causal asymmetry to explain, and it doesn't seem to me too big of a leap to assume that this causal asymmetry will also be explained in a similar way. I should contrast this with something else that's been talked about a little bit, which is the idea of zigzag causality, which I don't really believe in. So zigzag causality, okay, this is a sort of cartoon of it, but you imagine that an individual electron is going forward in time for a little bit, and then at some point it hits an interaction or a measurement device or something and decides, I know I'm going to reverse my arrow of time for a bit and then go back in the other direction, and then this kind of thing keeps happening. But I don't think that individual quantum systems like electrons in pure state really have an internal arrow of time. If there are arrows of time, they're emergent features of macroscopic systems, and so I don't think it really makes sense to talk in that kind of way. So that's why I'm talking about block universe theories rather than sort of zigzag causality theories. Okay, so a big motivation for what I'm going to do in this talk is, this thing that Hugh said a couple of days ago. So the idea was to rewrite the logic of Bell's theorem in this way. So, realism is an implicit assumption here, but quantum mechanics in the form of the observed Bell correlations plus locality implies retrocausality. So that's how he wanted to rewrite the reasoning. But I think that there are a couple of fairly big problems with this. The first is that, of course, and this has already been mentioned, in the standard Bell's theorem framework, no retrocausality is not a distinct assumption from things like free will, the idea that you can freely choose the measurement settings, or no superdeterminism, the idea that there aren't prior correlations between the measurement settings and the hidden variables. So they're all expressed by the same assumption, which is sometimes called measurement independence, just probabilistic independence of the hidden variables from the future measurement settings. So really all you can put on the right-hand side here is measurement independence. So ideally we'd like to separate some of these things. I claim that I've achieved that maybe a little bit to some extent in this. I'm not going to claim to fully resolve this problem. But the one that I am going to really focus on is this second one, which is this notion of locality here, assuming we're using a usual Bell's inequality proof, is going to be the usual definition of local causality that you use in Bell's theorem, right? If this is supposed to be a statement of the logic of Bell's theorem. But that notion of locality isn't really compelling in a theory which might allow for retrocausality. That assumption says that things in the future, so the measurement outcomes, the correlations between them are screened off by things in their past, right? So the local choice of measurement settings and the hidden variable state. Those are things that exist in the past of the measurement outcomes. Now, this is a very odd kind of assumption to make from a sort of time-symmetric block universe point of view. Why aren't we saying that things should also be screened off by stuff in the future? Or if we don't think things should be screened off by stuff in the future, why are we saying they should be screened off by stuff in the past? So really what we need is a more time-symmetric definition of what locality means, because in a theory which we hope to be time-symmetric and perhaps includes retrocausality, that would be the kind of notion of locality that we would want. So that's what I hope to achieve, is sort of re-understanding the logic of this statement in terms of a notion of locality that's more like that. If we want to prove this kind of statement in general, then we need to be adopting a framework that's independent of the specific details of quantum theory. Right? So the standard Bell's theorem, what we want to say is that you can go out there and do an experiment, and if you observe these correlations, then you have non-locality. And that's independent of the precise mathematical formulas of quantum theory. So if we want to support a general conclusion like that, then we're going to need to frame this in a sort of generic framework that doesn't assume quantum theory from the outset. So a few other motivations that I want to talk about briefly. So we've seen over the past couple of days, and we will see some more of them, that you can write down quantum theory or alternative versions of quantum theory that seem to involve retrocausality. So we've heard lots about two-state vector formalism, transactional interpretation, presumably Ruth's going to talk about. I don't know if she's here today. And we've heard about Ken Wharton's models. Now, none of these models obviously prove retrocausality, because at the end of the day, they're aiming to reproduce standard quantum theory, which we know we can write in different ways. The mathematics of it is just suggestive. So I would caution against drawing any strong conclusions from any particular mathematical formalism. As scientists, we're supposed to be skeptics, so this is kind of a skeptical position about that. Any physical theory will have multiple mathematical formalisms. So, for example, in classical physics, you can write down the Hamiltonian formalism, in which it looks like things are nicely evolving from past to future under local interactions, and everything's all nice and causal. You can also write down the Lagrangian formalism and the principle of least action, in which it looks like you're doing some global optimization over the whole of space-time. And you might think, well, that thing looks horribly non-local and non-causal and all this kind of thing. So I don't think that we should phrase principles in terms of any one mathematical formalism like that. So I would criticize the fish principle, which I don't think it was defined fully in Hugh's talk, but it stands for Feynman integral symmetry hypothesis. Now, really, it doesn't. The actual principle itself, I don't have too many problems with it because it's not really dependent so much on the details of the Feynman integral. But as it is, it's phrased in terms of a particular mathematical formalism. And I would argue that our argument should rely instead on mainly the operational predictions of the theory, which is the stuff that all the formalisms must agree on. And so in the pub last night, I think it was Chris Timpson who came up with this acronym, which I call the counter-hypothesis of instrumental prediction symmetry, or CHIPS. So that's the alternative to fish. I'm not going to say too much more about that, but this principle is really what's going to underlie what Matt Pusey is going to say in his talk, although he may decide to phrase it in a different way that makes this look rather silly, but we'll see. The other thing is we'd like to develop toy theories to illustrate how aspects of quantum theory can be accounted for by these kind of models. So one of the inspirations for this work was certainly the Helsinki model, which Hugh Price came up with. And the idea there is that we replace the idea of dynamics with sort of constraints on space-time. And so I'm really going to take that idea and run with it. So hopefully, eventually, this framework I'm going to present will include a viable approach to the whole of quantum theory. I'm not going to claim that I'm anywhere near doing that. What I'm really going to do in this talk is throw a bunch of definitions at you. But I think they have the advantage of being the right definitions. So hopefully that will be enough. Okay, so I want to deal with the operational predictions of the theory. I want to formulate both operational theories and the underlying realist models in a kind of more block universe framework than we normally do. So I'm first going to briefly go over what are called operational circuit models. So these have been developed by Lucian Hardy and by the group in Pavia of Mauro Dariano. And I'm going to present a sort of variant of that. That's a way of presenting the operational predictions of a theory that's more sort of a priori, doesn't have any time asymmetry in it. And then I'm going to explain how you can formulate underlying theories of reality that aim to reproduce the predictions of these theories. And then we can talk about the definition of locality and how we might identify whether these theories are retrocausal. Okay, so in a circuit model, the basic element is a gate. So I should say at this point that I'm not trying to make any claim here that the universe is a giant computer or anything like that. I'm really using these models as a kind of toy discrete model for physics going on in space-time. You could formulate the kind of stuff I'm going to say in terms of a continuous space-time, say Minkowski space-time instead, and then you would talk about constraints on regions of space-time. It's just a bit more mathematically complicated to do that. So here I want to focus on a kind of simple toy framework, but I think it wouldn't be too much of a problem to generalize. So the idea of a gate is that you can think of it as a single use of a piece of experimental apparatus. So put some experimental device on my lab table, and it has a number of, well, they're represented as input wires and output wires. So you just think of those as apertures. So perhaps I can plug an optical fiber into this device, and photons go in, and they come out at the other side. Okay, although this is called input wires and output wires, that's merely a sort of conventional terminology. The distinction between input and output is going to be more blurred in this framework. The wires also have a system table type label. So, for example, a qubit might go in here, and a three-dimensional quantum system might come out there, and those system type labels just refer to different types of physical system that there are. So potentially, as well as all of this stuff, each gate could have some kind of classical readout on it. Okay, so each gate is generally going to be associated with a random variable which takes a finite number of possible values. So the important thing to note here is that the gates, or the choice of gate, is supposed to be the thing that's under the control of the experimenter. So if I write down the gate H instead of the gate G, that can correspond to two things. It can correspond either to taking out this entire piece of apparatus and putting something else in, or even if there's just some settings which are under the control of the experimenter, if I have a knob on my device and I switch it from one position to another position, that's going to correspond to replacing the gate G with the gate H. So these correspond to the choices that the experimenter has available to them. And the random variables associated to the gate correspond to the things that they don't control. So these are the outcomes of the experiment. Okay, so I'm generally going to associate a random variable with every gate because it's just easier to do so, but some gates will only have one possible value. That means that they don't have a classical readout. The probability of getting that one value is always 1, and it's just a transformation. So something like a unitary transformation will be represented like that. So then I just need a notation to denote the sets of input and output wires and the set of wires, the total set of wires that are incident on a gate. Okay. Now there's a couple of special types of transformations. If a transformation has no input wires, so a transformation, this means it doesn't have a classical readout. Okay, so that just corresponds to a preparation. In quantum theory, that's going to mean prepare a system in a given state. And if it's a general gate, if it has a classical outcome as well, then it corresponds to an ensemble preparation. So it means flip a coin, depending on the outcome of that coin, prepare one of a number of different states. And for some reason, we usually denote preparation gates with these rounded edges, so I'm going to do that. Similarly, if you have a transformation, so this is something that has no readout with no output wires, then that's sometimes called a unit, and what it corresponds to is throwing the system into the trash. Sorry, I'm in England. It corresponds to throwing the system into the rubbish bin. And a gate with no output wires, so if it's a gate, it's got a classical outcome, then that corresponds to a destructive measurement. So I perform some measurements on the system, and then the system gets absorbed or thrown away after the measurement.
What are the rounded corners?
For some reason, it's just conventional to denote preparations and measurements with rounded corners. Everybody does that.
So it looks like Bob's one and Bob Cookie's one.
Yeah, I mean, I don't know that exactly. Okay, so this isn't going to be particularly important for this talk, but this is just to give you an idea of if you wanted to put quantum theory into this kind of formalism, this is what it looks like. So system type labels correspond to different types of Hilbert space. The input wires are going to get associated with tensor products of Hilbert spaces on all of the wires. Output wires, similarly. Preparation corresponds to a choice of density operator. An ensemble preparation, an ensemble of density operators. The unit is just tracing out a system. A measurement is do a POVM and then get rid of the system. A transformation, so no classical outcome in general, is just going to be a completely positive trace preserving map. So a unitary would be an example of that. And the most general thing is a gate, and that's going to correspond to something called a quantum instrument. And these are all just special cases of quantum instruments where some of them have a trivial classical outcome, some of them have trivial input space or trivial output space, but they're all subsumed into this general idea where you have a transformation which depends on some classical outcome. So I don't really want to go into the formal definitions of these things because this isn't too important, but just in case you're sort of lost on how these things are correspond to what you know about quantum theory. Okay, so now we can talk about circuits. So if you take a tuple of gates, so this just means an ordered list of gates, then because I have an ordering, instead of writing xgj for the variable corresponding to gj, I'm just going to call it xj, similarly for these wire sets. And then I'm not going to define this really formally, but you sort of know what a circuit wiring is if you've ever seen a circuit diagram. It's just an identification of output wires of each gate with the input wires of other gates, such that the system type labels have to match. There's no dangling wires that go off to nowhere, and there's no causal loops. So this is an example. It's just the usual sort of computer science notion of a circuit. So a circuit is just a tuple of gates. So this is this tuple of gates associated with circuit C, together with a wiring, and I'm going to use WC to denote the set of wires in a circuit. Similarly, XC denotes just the ordered list of random variables associated with each gate. So when I say probability of XC, I really mean the joint probability of all of these things. Okay, so now an operational circuit model consists of a set of gates, right? So given a set of gates, there's a bunch of different circuits I can form from them. So from my set of gates, I can pick a bunch of different gates, I can form tuples of gates, and they pick the same gate twice here and there. So there's a bunch of different sort of ordered sets of gates I can create from that, and some of those tuples will have wirings, some of those will have good wirings, and allow me to form circuits. So every circuit that can be formed in such a way, my theory should predict for me the outcomes of all the random variables given the gates that I've chosen. Okay, so here is just an example of a circuit, and this is, if this was a quantum mechanical circuit, this is how you write down the predictions that quantum mechanics makes for that, right? So we have a couple of preparations, which are potentially ensemble preparations. They correspond to sets of density operators and probabilities. We've got a couple of dynamical, generally quantum instruments, and then we've got PAVM and chucking the system away.
Sorry, what exactly are you conditioning on with the calligraphic G? Or
this is the set of gates, this is the tuple of gates. So remember the choice of gate is supposed to be analogous to the measurement setting. So if I've got a gate G, I can replace it with a gate H, right? And so I want to condition on those things because I'm thinking of those as being like measurement settings. So GC was the tuple of gates.
But it doesn't specify a wiring.
Well, this is supposed to be the probability associated with the circuit C. Yeah, so that's all specified. So maybe I should have conditioned on the whole C here, but really I'm not going to, when I talk about things like Bell's theorem, I'm going to talk about changing gates and not changing wirings.
Okay, so but it has the full information of the circuit in it.
Yeah.
Is there a notation for this setting choice or not? Sorry.
So the setting choice is here. This is what I'm conditioning on. This is the set of gates that form the circuit. Okay. So the choice of setting means change gate G to gate H. Okay. Right. So that's in there.
And X is what?
X.
X1, for example. That's the
random variable associated with G1.
That's the classical random.
The classical random is the outcome. It's the classical readout on that particular gate. Does that make sense?
Just before, I thought you were talking about flipping a coin and making a particular preparation. Is it that coin?
Just imagine that happens all in terms. That whole process is like put in a black box, which is the gate that we call G1.
So it might or might not depend on the inputs to that gate.
Well, if it's a preparation, preparations have no inputs, so the random variable necessarily is just a pure.
Yeah, but if there are inputs, then it might not.
It may or may not. I mean, you can always do the measurement, which says completely ignore the system and do a coin flip. That's a valid PAVM.
Yes.
So you could have that kind of thing happen. Okay. So this is just a quantum example, but in general, in the general framework, I just have these probabilities, and these are the operational, the observed probabilities, and you should probably want to impose additional causality constraints on them, such as that at the operational level there should be no signaling into the past. And the ways of doing this have been laid down in great detail by Lucille and by the Pavia group, so I'm not going to go into that because we're mostly interested in underlying realist models. But just bear in mind that those kind of constraints are expected to be built in. Okay, so now what we want to say is that's how we describe the things that we can observe in the lab. Now we want to say, okay, there's some real stuff that exists out there independently of us, and that's really responsible for what we actually observe, and we want to know how can we describe that sort of stuff. So this is like the conventional idea of a hidden variable theory, except we want to do it in a more block universe way, where we don't assume any predefined direction of causality. Okay, and I probably should have said this before, but we're going to at some points have to consider when circuits are of the same type. So if the wiring of the circuit and the system type labels on all of the wires are the same, I'm going to call them circuits of the same type. So for example, if I replace this gate here, G3, with a gate H, which happen to have the same kinds of input wires and output wires, that would lead to a circuit of the same type. But if I put in a different gate here, which has, say, a different number of output wires or a different system type labels, then that would not be a circuit of the same type.
Sorry to interrupt. These random variables X,
yeah.
Do they depend on the input wires?
So in general, so think about the quantum case. So in general, a gate's represented by a quantum instrument. So that represents a measurement together with its update rule. In that case, the X would be the outcome of the measurement. So it would, in general, depend on what state comes in on the input wire.
So these X variables X are not independent because some of them will be.
No, they're not supposed to be. Okay, so now if we want an ontological model, that's going to consist of several parts. So the first bit is we need a probability space. So this lambda here is supposed to be the set of states of reality. This is just a sigma algebra so I can find probabilities, and then I'm going to have a probability measure on that. Now, I should say here that at this point, I don't want to assume anything about locality. The whole aim of this is to tell you what locality should be, what the assumption of locality should be in this framework. So I have to start out not making the assumption of locality, and that means that these ontic states don't live in any particular location in the circuit. There's just some global lambda. I'm not saying anything about whether it's localized or anything like that. There's just some state of reality which is associated with the circuit. Okay, so this is called the ontic state space, and this probability measure is just some notion of a uniform measure. So really, if you're dealing with a discrete a finite ontic state space, it's just going to be the counting measure. I just need some way of saying what the volume of a given set of ontic states is. But in general, if you have a continuous space, or if your space has some sort of topology, then there'll be some natural notion of that. So if it's a sphere, I'm going to use Haar measure over the sphere or something like that. So this is somehow it's some sort of a priori probability measure over the ontic states. Then the hard part is that given a particular circuit, I need a rule for computing the outcome probabilities in terms of all this stuff. And that should reproduce the operational predictions. Yes?
What's sigma?
It's just a sigma algebra. For those of you who don't like measure theoretic probability, just pretend that mu is a probability distribution and ignore sigma. So I'm going to define, I don't have much time to do it, but let's try to do it. I'm going to define two classes of model. which I call constraint models and probabilistic constraint models. Yeah.
So you could call lambda like a hidden variable?
Lambda is a hidden. This is supposed to be a generalization of the usual hidden variables framework. Yeah. I need to introduce probabilistic constraint models as well, because when I generalize Bell locality, it turns out that these are the guys that properly generalize the usual notion of Bell locality. So roughly speaking, these are going to be the analogs of deterministic hidden variable theories in the conventional framework. These will be the analogs of probabilistic hidden variable theories. But actually, when you get rid of the causality assumptions, both of these types of models will predict sort of probabilities between 0 and 1. It's only when you impose the usual sort of causality framework that you get that out. So a constraint model is formulated, as you might imagine, in terms of constraints. So each circuit, so in particular there are two things. So first, each circuit is going to be associated with a constraint, which is just a subset of the possible ontic states. So the idea here is that given that I've built this circuit of these particular pieces of apparatus, there are certain ontic states that are compatible with that and some that aren't. So gamma is just the set of ontic states that are compatible. If I have a specific set of outcomes, then that's also going to enforce a constraint. So, in the usual framework, you would have, the outcome being a function of the hidden variable that's being input to the device. So clearly, in general, knowing that we have a particular list of outcomes is going to impose further constraints on what the ontic state can be. So the basic idea is that in a constraint model, so each of these tuples of values is going to be associated with a constraint. It has to be consistent with the circuit constraint, so it should be a subset of it. And these should be disjoint, so this is the analog of, this is a more general analog of sort of the idea of determinism in the conventional framework. And of course, if we forget the outcomes of the circuit, then we should just get back to the original constraint of the circuit. So that's what these two conditions say. Okay, so now the operational predictions can be rewritten in terms of the hidden variables, if you like, or the ontic states. This is just applying the rule of total probability. And then, given this probability measure that we have, we can compute, and these constraints, we can compute what those things are. Since I'm running out of time, I'm not going to go through that in a lot of detail, but the upshot is that we just end up saying that the probability of getting this set of outcomes is just the a priori probability of the constraint associated with that set of outcomes divided by the probability of the global constraint. Okay. So now the slightly more general type of model is a probabilistic constraint model, and this is fairly straightforward. You just imagine that instead of being associated to a fixed constraint, a circuit is the constraint that applies on any given run of the circuit is drawn according to some probability measure. Right? So if you have a finite set of possible constraints, when you work out the mathematics of it, all it really means is that instead of this formula, you'll get a convex combination of such things. That's all that means. Okay, so now what I'm going to try and do is define locality to show how you can sort of simulate locality by a very sort of trivial example in this kind of framework, and then explain the relationship between locality and retrocausality. So basically there are two locality assumptions we want to make. The first is what's sometimes called Einstein's separability, or the idea that there should be local beables. If we have a separable model, what it means is that the ontic states have locations in space-time. They're located at points in space-time. So in this framework, what that means is that I'm going to have the ontic states live on the wires of the circuit. Okay. The ontic state space should decompose into a Cartesian product of individual ontic state spaces, one for each wire, and I'm going to have a lambda that lives on each wire of the circuit. this is just an aside, it's not too important here. You're probably going to want these ontic state spaces to only depend on the system type label. So the idea is that if you have a qubit on a given wire in quantum theory, then the ontic state space of the qubit should be the same whenever you have a qubit, right? You can construct otherwise quite convoluted models in which the size of the state space grows and you record more and more information as time goes along. Those are kind of contrived models. It's not going to play a role in what I'm going to say, but typically you'd want to do that. I also want to make a side note, because Joe's here, which is that because he wrote a paper on this, separability isn't strictly speaking necessary for defining Bell locality, either in this framework or in the standard framework. It does simplify matters to assume it, but I could, in addition to these local variables, have some notion of global parameters as well. But I'm not going to do that today because it's complicated things. Okay, so given separability, here's how Bell locality gets generalized. So, so if I have a separable constraint model, then this lambda j here is supposed to be the ontic state space associated with gate j, okay, gj. So the ontic state space associated with this gate is just the set of ontic states and all the wires that are incident on it. So these 5, okay. So it's just the wires. It's just the Cartesian product of the state spaces of all the incident wires.
But just the inputs?
No, all of them, because we're being symmetric here. There's no distinction between input and output at this stage. So I'm going to say that a separable constraint model is local if each gate is associated with its own local constraint. Okay, so now instead of having just global circuit constraints, I'm going to have constraints that are associated with the sort of local incident wires of a given gate, and those are going to satisfy the same sorts of assumptions, right? So the gate constraint where you don't consider the outcome is some subset. Each outcome is going to be associated with the subsets of that. Those have to be disjoint, and they have to give me back the gate constraint when I take the union over them. So the global constraints of the whole circuit then are really just the intersection of the constraints for each gate. Formally speaking, that's this. So what I mean is I take the constraint on the gate state space, I have to make it into a constraint on the whole space. So I do that by just putting the trivial constraint everywhere else, so the whole space. Take the intersection of all those conditions, and similarly for the constraint where you forget about the outcomes. Okay, and then I'm not going to write down the mathematics of this because it gets a bit hairy, but in a probabilistic constraint model, what you imagine is that now you do the drawing of the constraints locally at each gate. So each gate has an independent distribution of the local gate constraints, and the whole thing comes from drawing independently from each set of gate constraints, and then using standard formulas for that. So this is just to show you.
Sorry, a different wire the same wire can be in different gates. So how do you make sure you get the same constraint for each wire?
Well, you don't. The point is that the constraints have non-trivial intersections, right? So this gate imposes some constraint on its output wire. If that's also an input wire, then there's going to be a constraint coming from the other gate as well, and you're taking the intersection of those constraints. So it has to satisfy both constraints. Now, of course, there are sets of constraints you can come up with that have no solutions, and it's sort of implicit here that I want to deal with a set of constraints that does have a solution. Okay. Just to give you a simple example of how you can. I'm really running out of time. Okay. To give you a simple example of how you can get non-locality, this is like the dumbest model in the world you could possibly imagine to simulate a PR box. Okay, so correlations which violate CHSH inequality to the maximum possible extent. So here there's only one type of system. So each wire just has the same ontic state space. It's just 2 classical bits. And I'm going to label the first bit A and the second bit X. And the first bit is that you can think of it as the input, as one of the inputs to the PR box, and this is the output. Okay, so basically it's a fairly dumb model because the wires just contain, full information about the settings and the measurement outcomes. So just take the counting measure over that. So it just counts the number of different states. Now the PR box itself is just going to be represented by preparation gates. This is a transformation, technically speaking, so it has no outcome associated with it. So it just has one constraint. So that's going to look something like this. And its constraint is, those of you who know about PR boxes, trivial, just the PR box constraint. So here this is addition mod 2. So if I list the ontic states on this wire in this order, that corresponds to this constraint. It's just all the lists of these bits which are consistent with this. So kind of.
But that's not a circuit.
Sorry?
That's not a circuit.
This isn't a circuit, this is just a gate. And this is the constraint associated, this is the local constraint associated with that gate. Then I have to tell you about the measurement gates.
Right.
So there's a choice of setting. So I'm going to call the gates 0 and 1 because they correspond to choosing an input of 0 or 1 to one arm of the PR box. And those just correspond to like the trivial constraints. So this is gate when the gate is A, i.e. 0 or 1, and the outcome is X. The constraint associated to that is just you've got to have AX. And then when you take the intercept, so if you consider these circuits here, where these two measurement gates can either be this gate or that gate, then basically you just take the intersection of these constraints with these ones, and you otherwise have uniform probability. So, I mean, the calculation is fairly straightforward. You're just going to get the PR box correlation simply because you have this constraint here. And this model is kind of retrocausal because obviously these A's are telling you exactly what the measurement settings are, so that's why you can do this. Now, I don't really have time to talk about this, and it's not all that interesting anyway, but just to say that if you've got a PR box, you can simulate singlet correlations because as Sandhu and co-authors, I don't think Nicolas here today, but Sandhu and various co-authors showed if you've got a PR box, you can simulate singlet correlations using some extra shared randomness. The only thing I want to say about doing that in this model is you can, if you formulate that model in this framework, you can make it such that full information about the measurement directions that you've chosen aren't actually present in the ontic states on the wires. So you do have some information on the wires about what the measurement settings is, but it's not full information. So if you just convert their model into this framework. Okay, so I've only got a few minutes left, so let me briefly talk about retrocausality. So first of all, how is all this related to the usual notion of Bell locality? Well, basically, if you talk about a constraint model, I'll say it's causal. So this is sort of the usual sense. If every gate, the constraint associated to every gate, so ignoring the outcomes, so just global gate constraint if it's a function. So that means each value for all of the input wires is associated with a unique value for the output wires. It's just the usual notion of a function. So if that constraint is a function, then that means that when you ignore the outcome, you can think of the transformation as deterministic, function from input to output, and in general you can think of it as a deterministic function where the input wires determine uniquely what the outcome is as well. Similarly, for a probabilistic model, you'll say it's causal if the probabilities are non-zero only on constraints which are functions. And this means that the transformation is just going to act like a stochastic transition matrix from input to output. And it's fairly easy to see that if you do that, then causal local models, in this terminology, are going to satisfy Bell's usual definition of local causality. And this is the sense in which constraint models reduce to deterministic local hidden variable theories, probabilistic constraint models become general, possibly stochastic local hidden variable theories. So if you want the general Bell condition of local causality to come out, you need to adopt the probabilistic constraint models. So this is a true generalization of Bell's local causality. It reduces to it in a certain context, and it sort of has this time symmetry built into it, and it does place a non-trivial constraint on the set of possible theories that you can have. However, we're not quite yet done with the relationship between locality and retrocausality. So hopefully I can take a couple of extra minutes to talk about this. So this is easiest to do with an example. So how would you identify when something's retrocausal in this framework? If I take basically two copies of the same circuit and I replace one of the gates. So this corresponds to choosing a different measurement setting. Then I can sort of talk about the backward light cone of this gate. It's all the set of ontic states which I can reach by traveling along wires backwards from this gate, and similarly the gates that are kind of in its backwards light cone. That's these ones. So these are the lambdas that are associated with that. These are the random variables. And then we can say that a model is retrocausal if the probability over everything, the outcomes and the ontic states in the backward sort of light cone, depends on whether you've chosen gate F or gate H. So you can formulate that in general for sort of any circuit and changing any one or any set of the gates. So obviously causal models are not retrocausal in this sense. They satisfy Bell causality. PR box and singlet models are. However, there's now a question. If I have a model that isn't causal in the sense of functions or stochastic transitions, are those models always going to be retrocausal? The answer is no, because so this again is something that I mentioned earlier. So the idea that there could be very different mathematical formalisms for the same theory. The same is true here, right? So here's just a simple example. If you have, this is basically just a simple transformation gate, so no classical output with an input and an output that are just classical bits. So if my constraint model for that is this, well, this constraint is just no constraint, so every possible input and every possible output are allowed. So I'm just going to get probability of a quarter of each of these possible things. But that can also be simulated by a probabilistic causal model, where you imagine that this is a stochastic transformation which just flips the bit with 50% probability and leaves it alone with 50% probability. So if there's no constraint on lambda 1 as well, then that will give the same probabilities. So obviously, since this has a causal model, so if I have a bunch of gates that are sort of like this, so they're formulated in terms of constraints which aren't causal, but I can rewrite them as probabilistic constraints, then obviously that's going to satisfy Bell causality as well. So I'll call such models implicitly causal. Now I haven't quite managed to prove this yet, but I think it's the case that if you have a model that isn't implicitly causal in this case, in this sense, then it must be retrocausal. So if that's true, then now I can go back to the beginning, and the locality in the implication that you had, I can take to mean this generalization of Bell locality, and then if that conjecture is true, you can really prove this. So the quantum correlations plus locality would imply that your model has to be non-implicitly causal, because implicitly causal models must satisfy Bell causality. And then that would imply, if my conjecture is true, that the model must be retrocausal. Okay, so since I've gone a bit over time, I'm going to leave it there. So thanks for your attention.